All right, hi everyone, I'm back. My name is Jack Koenig. As I mentioned previously, I was previously a Berkeley grad student, and I'm now a software engineer at SiFive. And I'm here to just kind of talk about Chisel 3 and FIRRTL and tools that we have been building in the open source community on top of them to help raise the level of abstraction. So I guess this talk is originally a longer talk, so I'm going to have to go fast. But the first question is, why are we doing any of this? And the original motivation was so that a group of people about this large could build lots of chips. You'll notice I'm not in this picture. This predates me at Berkeley, but the basic idea was that a handful of people can build chips productively. You already saw this picture, but this one might be more up to date. These are the chips that have built at Berkeley. Note that this excludes SiFive. It excludes any other external people using Chisel. This is just the research group at Berkeley. And so when you look at those types of results, you're going to wonder, like, how? How can you do that? And what we believe is the real way that we accomplish this is through Agile hardware design. So just like Agile software design made software developers more productive, we apply these techniques in hardware. Hardware is usually waterfall. Developing new hardware is hard. It's kind of in the name. And that involves a lot of things like architectural design space exploration, RTL development, verification, did we build the thing right? But also another term that we use a lot is validation. Did we build the right thing? I know these terms are different at different places. There's a lot of overloading, but that's the way that we use it. And it's really important when you're building something, if it's going to take you a few years to go to market, you need to know that you built the right thing for the market in 3 years. So part of Agile design is you can iterate and you can more quickly see what does your power look like, what does your performance look like as you develop, and you always have something ready to go. The real thing that's important here is to attack NRE costs, which requires a faster design cycle. Designers need to be more productive, which involves doing more with less code and leveraging libraries. So basically, the whole idea of all of this is to enable Agile hardware design, which involves writing reusable code. So a problem you might come up with is parameterization, right? Like, can you make the dcache bigger when you have this design? Can you make the floating point optional? Can you turn off cache coherence? And the problem is that these things are really hard to do with a standard Verilog parameterization system. And so normally you start with Verilog, you then say, okay, that doesn't work, so we're going to generate Verilog using something like Perl or Python, just kind of concatenating strings. You quickly run into problems because the metaprogramming language and the hosted languages are different, and you only find problems late in the compilation cycle, and it's kind of hard to trace back to what caused it. And we also, you can get into debates about languages, but we think that static typing is helpful, which is a feature of Scala and not of Python and Perl. So this is where Chisel, which we are all here for, most of us probably know what this is, so I'm going to go through this very quickly. It's not HLS, it's a domain-specific language where the domain is digital design. When you have your hardware constructs, they are just types in the language. Since Chisel is embedded in Scala, the metaprogramming language and the hardware construction language are the same, so you should not run into problems where you run into errors way late in a VCS compilation error. And importantly, and as you've seen in this session and throughout this whole conference, it's intended as a platform upon which to build higher level abstractions. And that's the real goal. Chisel is not the end in itself. The idea is for people to build cool, powerful things on top of it. There are a lot of related HCLs. There's a ton in Python. There's another one in Scala. So now I'm going to talk a little bit about decoupling design from implementation. So you have this design. It's like, can you punch SRAM ports all the way to the top? Sorry, I don't actually know what the final hierarchy is like, so I can't really do that quite right. And also, we may need to change the SRAM configuration. It may turn out that a skinny and tall one is better than a fat and wide one. And the problem is, if you aren't ready to make these decisions early on, it's important that you can decouple them from the actual, decouple the logical design from the implementation in whatever technology. So the problem is that there's things you need to do to hardware that are orthogonal from the source code describing the functionality, and so you want to separate the concerns of design and implementation. Traditional approach is you just manually do it, and every time you change it, you just get ready. Hopefully you're really good at Vim macros or Emacs, and you can change it really fast. You may use tools like PyVerilog or something to help with the mechanical work, which is a big step forward. You may write your own tool to do the same thing. But in our experience, these types of techniques tend to be brittle, and it's better to do this in a more principled way. And so how do you do that? You borrow good ideas from software and build a compiler. You'll probably see this slide again, because I stole this slide from Adam, but it's a very good slide. And the basic idea is LLVM allows you to have all kinds of different projects and languages and compile them to x86, to ARM, to RISC-V. And so why can't we do the same thing with hardware mapping to simulation, FPGAs, and ASICs? And that's the basic idea of what FIRRTL does. Sorry for flying through this. So FIRRTL is pretty cool. You should check out some more information on it, but I'm going to get to a couple of abstractions that we're building on top of all of this. One of the goals is to build an ecosystem, and so Chisel and FIRRTL are important aspects to it, where you have the higher level abstractions and then the ability to decouple design from implementation. So now let's talk about some higher level abstractions. So this is something I'm calling parameterization plus, which is you've got this design and your boss comes and says, hey, can you add a UART for me? And you're kind of like, well, sorry, like we've been working on this for 2 years and that has implications across the whole design. The thing is that many parameters of the SOC are only known once you know the full topology of the SOC. So for example, with a crossbar, you can only synthesize the address code once you know all the address sets that are visible downstream. Now, of course, you can always parameterize things in a very top-down fashion where you call out everything in the design, everywhere it's going to be, all the addresses and all of this. But we find that that's hard to scale. It's hard to reason about. And it's much easier if you can just describe things in a simpler way, like I just want a UART, and the UART knows how many addresses it needs. And then it adds that constraint to the overall design, and then you can emit working Verilog. Other things are physical memory attributes and protection and stuff where it depends on what devices you have downstream for what characteristics you have, say, in the cache for different memory addresses. So how do you build an abstraction to do this without worrying about other parts of the system? Well, you rewrite the crossbar every time, or you buy a crossbar generator, which is a pretty common approach and is much more robust to change than writing it yourself every single time. And the answer that has been built on top of Chisel is called diplomacy, which many of you may have heard of. It provides a node abstraction. It's kind of a logical view of the circuit separate from the module hierarchy. So you think about the module hierarchy as the actual Verilog that you're going to be taping out, but diplomacy is a level above that. It is the logical abstraction where there are two phases. There's negotiation and elaboration. So negotiation is where you declare your graph and describe the nodes connecting things, like this is connected to the crossbar, that's connected to the crossbar. And then elaboration is once you've set up that entire logical graph, the parameters can be calculated based on the constraints added by each piece in the logical hierarchy. So a little bit more about negotiation. During the negotiation phase, one set of parameters flows outwards from masters to slave. One set flows back from slaves to masters. So it's a pretty simple, just two passes there. And then adapter nodes in between can modify parameters as they flow through them. So you can imagine you may have, people who need a bus. They don't really care about the width, but you just pick 32 bits as your data width. Well, later, you may be going off chips. You may need to reduce that width, or you may just be going to longer wires where it's more expensive or whatever, and you may either increase or decrease that width. So your adapters can change those widths or any other parameters. And they can also place constraints on those parameters in order to build a system that makes sense. So really the goal of this is to dry out parameterization where every piece of knowledge must have one source. So here we have a crossbar and it needs to know that there's 3 people connected to it. The other crossbars need to know that there are 3 people connected to it because that has to do with the address width. All of these need to know that width because it has to do with how wide the address width is. And here's 1, 2, and 3. So basically we can make that simpler by just saying, here are the 3 things connected to that node, and then everyone else will just use derived parameters from the diplomatic calculation. I'm going to skip through this, but a lot of things can be diplomatic. Cardinality, address widths, ordering requirements, other stuff about, I'm sorry, I'm blanking right now. But here's a real diplomatic graph where we have tiles, peripherals, other stuff. I have a whole nother one. All right, 40 seconds, let's go. So we also want to be able to decouple design from implementation with our parameterization. So it's like you have a design, can I put it on a VC707? All right, let's build a wrapper. All right, what about a VCU118? All right, let's build another wrapper. Okay, now about another vendor's FPGA. And you're like, seriously? The basic problem is that you need a wrapper for every FPGA, and this is kind of an n times n problem where every design you have for every design out of n designs and every FPGA out of m FPGAs, can you map them across that? And we really don't want to do it that big or have that large of a space. So instead, normally people limit themselves artificially. But instead, we have FPGA shells, which have shells and overlays, where a shell is an interface for an FPGA, which exposes what the FPGA features are. There's no negotiation. This is really just specifying in an object-oriented way what features are available, and the design uses it uses the interface that a shell could provide to determine what things it needs. So as long as the FPGA has a shell appropriate for the resources you need, like clocks or other I/O, then it will still map properly. And it can generate constraint files for the FPGA as well to help simplify that problem. So yeah, sorry that I had to fly through that, but anyway, please get involved on Stack Overflow, Gitter, mailing lists, everything. Thanks.
So once again, if you have questions, please come up to the mic. I'll start us off with one. Do you see diplomacy as being a pattern that's widely usable outside of Rocketship even? And I guess furthermore, how do you think diplomacy is going to interact with like other pieces? In particular, as a user of diplomacy, I find error messages are always like, the very nature of what it's trying to do makes error messages hard. Do you have other like thoughts about using diplomacy with other stuff, especially outside the context of Rocketship?
Yeah, sure. So, I mean, diplomacy, a lot of the problems with diplomacy are pretty historical for pragmatic reasons. I mean, diplomacy has been tied very heavily to TileLink because that was what we needed to get working. I think it's a more generic pattern that should extend beyond TileLink. I think it's also potentially possible to have it be multi-language. Like, I think it's a way to link generators. It's only a two-stage process, so it's not like you have to be calling between the different languages a lot. You go once for negotiation, and then back, and then once for elaboration. So I think it's a good pattern to apply in a wider context. I think that there's just refactoring work necessary in order to make that easier to do.
Hi, Derek Lockhart, Google.
Hey.
So you gave us a list of things that could be diplomatic.
Yeah.
Do you have a list of things that cannot be diplomatic interfaces?
That's a great question. I'm not sure about what can't be diplomatic. Yeah, I guess I'd have to think about that and get back to you offline. Sorry.
All right, let's thank the speaker.